Okay, so apparently there was this city of Konigsberg, which is now in modern day Russia, um, had seven bridges like this. So you had like, these were land, there was a river going through the city, and people would walk over these bridges. And one of the questions that people had was like, is there a way for anyone to cross these bridges exactly once and come back, but not going through any of the bridges twice? That was a puzzle. Like here, here. No, that doesn't work. Yeah, you can try every possibility, and it doesn't work. And in 1736, uh, a famous mathematician named Euler looked at this problem and decided that this is not possible. Okay. Let me try to explain how this is related to graph theory, and then we'll start from there. Okay. So first of all, let's think about these places as nodes. So let's just say this is A. Let's say B, C, and then D. Then you have, let's say this point is A, and then 2D. There are two edges connecting them. So because there's more than one edge connecting two nodes, what you get is not a simple graph, it will be a multi-graph. Okay? And yeah, I won't. Let me draw this again. Well, let me draw it here. Okay? So here's, let's call this A, and there's two things going to D, and two going to this another B. And then B and C are connected by one edge. And then C and D are connected by one edge, and A and C are connected by one edge. Let's make sure that we didn't miss anything. So there are 1, 2, 3, 4, 5 edges coming out of A. D has 3 coming in, 3. And C, there are 3 connected to C. Okay, that's good. So that's what you have. Okay? So you can simplify the graph this way, and you get a multi-graph, not a simple graph, because there are more than one edge connecting two vertices. So you can rephrase the question as, can you draw a walk that goes through every edge and you come back? Is it possible? Okay. Or you might even weaken the question like, you don't have to come back. Is there any way you can go through every edge and you don't repeat any of the edges? That could be another question. Okay. So that gives rise to something known as the Eulerian path. So definition. An Eulerian path is a walk that goes through all the edges exactly once. And an Eulerian circuit, or Eulerian cycle, is an Eulerian path that it begins and ends at the same vertex. Begins and ends at the same vertex. Now, we have to be a little careful about the terminology here. Last time when I was talking about walk and path and cycle, I said that walk is anything that you start with a vertex, edge, vertex, edge, vertex, edge, right? And you end at a vertex. And you can repeat the edge, it's okay, right? So that's a walk. And I said path is when you do not visit the same vertex twice except when it's beginning and the end. And cycle is a path that begins and ends at the same point. That was my definition. But see, if we try to do an Eulerian path, you end up having to come back to the same thing, right? So you don't want that limitation here. So because of that, some books will try to say Eulerian trail, and by trail, the definition is like a walk that does not repeat any edges. Okay, so Eulerian trail is a trail that goes through every edge. So no repetition, but goes through every edge. That's like how some books would define it. And they would also use cycle as circuit interchangeably. So instead of saying Eulerian cycle, they might say Eulerian circuit. Yeah. So there's like slight difference in the terminology, but since Eulerian path and Eulerian circuit or Eulerian cycle, those are pre-established words. Even if Eulerian path is not a path according to our definition, we'll just accept that as it is. Okay, yeah. All right. So, so in other words, depending on the textbook, there are slight differences between the definition of what a walk is, a trail is, a path, and cycle, and circuits, and all that. Okay, so just be aware of that. But when people say Eulerian path, it means this one. It's never any difference. Okay. So now, in order to think about how to argue where such and such is possible or not, let's just think about every way you can draw a path that can be like drawn without lifting your pen. So let's say you start from this one vertex. So this is like the most trivial graph there is, where there's no edge, there's only one vertex. Okay, now let's think about something that has two vertices. Yeah, there's like if you have two vertices and an edge, this is the simplest you can go. Now, because we're doing multigraphs, you might be able to do this and come back, something like that. How about three vertices? You go like this, this, and this, right? And then you realize that if you're trying to draw a graph through many vertices, so let's say you have something like this. If you try to draw a graph with many vertices, every time you go through a vertex, you have to go into it and you have to come out of it, right? Yeah. So the number of ingoing and the number of outgoing edges should always equal, right? So here's an example. here's a nice analysis of this. Okay, let me give you some time to think about this. Suppose you have a graph like this. Okay, you have a graph with 1, 2, 3, 4, 5, 6 vertices and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 edges. Can you find an Eulerian path? It doesn't have to be a cycle. Okay. Can you start somewhere and end somewhere else, visiting every edge possible? All right, so continuing my observation, think about this. I just said, oh, everything should have an incoming and outgoing. However, look at the beginning. This one only has an outgoing and then this one only has an incoming, right? So when the beginning and the end are different, then you don't have to have the same number of outgoing or incoming. Okay? So what that means is that if you count every edge coming out of a vertex that's incident with the vertex, the number of edges that are incident with the vertex, that's called a degree of a vertex, right? So how many edges are connected to this one? 3, right? How about this one? 1, 2, 3. So 3. How about this one? 4. How about this one? 1, 2, 3, 4. 4. 1, 2, 3, 4. That's 4, and this is 2. So what you observe is that these are okay. 4, 4, 4, 2. They're even numbers, so you can say 2. So for example, if you have 4 of them, you can have 2 of them incoming and 2 of them outgoing. Right? However, these ones are odd, so that must be the case when you begin or end. Okay? So if you were to draw this entire thing without lifting your pen and without going through the same edge twice, you see that it must be starting over here and ending there, or vice versa. You could start here and end there. Okay? So there should be something that does that. So let's try it. Do this, that, that. Oh no, I can't come back here because then it'll be ending. So so if I start here, I have to try not to visit this as much as possible. Okay. So, oh, but it's okay. Okay, sorry. It's okay because I can go in and then go out, but then at some point I have to come back at the end. So I do this, go here and then go up, go here, go there, and then go there, go there, and I end that, and that's done, right? See? So let's see. Right? So I drew this without having to lift my pen, and I visited every edge exactly once, right? Okay, so that's the Eulerian path. I just described the Eulerian path. Okay, so this is an example of a graph that has an Eulerian path.
Wait, can you do it one more time?
Right?
Yeah.
I visited every edge exactly once, right? Okay. Yeah. So, but on the other hand, if I just had this time it won't be possible to draw this in any way. This won't have an Eulerian path. Why is that? Why won't this have an Eulerian path?
It doesn't have the two on top.
Yeah, it doesn't have this point. What's the role of this point? Well, it makes the edges on the top even. So here you have 3, 3, 3, 3. And if we say this is a vertex as well, then we have 3, 3, 4, 3, 3. So you have 4 odd degrees, 4 vertices of odd degrees. And that means it's impossible. What that means is that I can draw this by using 2 Eulerian paths. So I can make one that does this. No. Yeah, I can do something like this. And then, so that's one. And I can start from here and do, yeah. So I can, if I start and begin at one point and there I would need two drawings to have one. Okay? Yeah. So this one wouldn't have an Eulerian path. Okay? So by investigating how drawings can be done, and by looking at the simple fact that if you draw through a vertex, that means there's an incoming, there's outgoing, so you better have the same number of edges connected to one vertex, right? So because of that, Euler proved the following, that a graph has an Eulerian circuit if and only if all vertices, so all nodes have degree even, or even degree. Let's write down even degree rather than yeah. If you want to start at some place and then come back to the same place, visiting every edge, then it has to have an even degree. Okay? And then for a graph has an Eulerian path, if and only if, by the way, this is the way you write down if and only if. So if and only if there are exactly 2 or 0 nodes of odd degree. So if it has 0 nodes of odd degree, that means everything's even. That means that we will have a circuit, Eulerian circuit. But if it has exactly 2 nodes of odd degree, that means you would have an Eulerian path that starts from one odd degree and ends at the other odd degree. Make sense? Okay, so that's the simple solution that he came up with, and then came back to look at this graph and said, hey, this is degree 5, this is 3, that's 3, that's 3. So what does that mean? There's no way you can, there are 4 vertices with the odd degree, so there's no way that can happen. But then you see that once you delete one of the bridges, then the degrees work out and you have an Eulerian path. So if this bridge was deleted, then suddenly you have degree 2 here and degree 4 there, right? These are still odd, but there will be an Eulerian path where you start from here and then you go through every bridge exactly once and come back to this place. So that's the observation. So that's a solved problem. While this was solved just by observing every possible way you can draw a graph, Uh, there's another similar notion where we don't have a criteria for. So let me talk about a second definition, which is definition. A Hamiltonian path is a path that visits all vertices exactly once, except for the last one, except for the last vertex. So the last vertex could be the place that you started with, okay? Hamiltonian circuit or Hamiltonian cycle is a Hamiltonian path that is a cycle. Being a cycle means you begin and end at the same place, okay? So that's the definition. And this is easily seen to be Hamiltonian, to have a Hamiltonian cycle, right? You can start from here, go there, and then come back. Okay? You visit everything. You can, in other words, to be a Hamiltonian path, it doesn't have to be, you don't have to go through every edge. You can just take some edge. And this has more application because this is also known as the traveling salesman problem where you're trying to go through each city and then visit there and then you sell stuff and come back, right? You have to visit every city, but then not every city is connected. So you may have a situation where there's only one flight from city A to B, and then city B could be isolated or something, so that you may have to go to B and then you have to come back. So you have to visit the same city twice, right? So we say a graph is called Hamiltonian if it has a Hamiltonian circuit. If you can go through every point and come back, that's called Hamiltonian. That's called Hamiltonian. So here's an example. Okay. Let's say you have 4 cities that have connecting flights like this. So there's A, B, C, and D. Then there's a flight from A to D, A to C, A to B, and there's a flight from B to C, B to A, B to D, and so on and so on. Okay. Now, for this graph, the question of Eulerian path would be: can you take every flight exactly once? Okay. Yeah. If that's possible, then there will be an Eulerian path. Right? But look at the degrees here. What's the degree of this? What's the degree of A?
3.
3. This one?
3.
3.
3.
3. 3. Okay, so does it have an Eulerian path? The answer is no. right? Because you have 4 odd degrees. So it's not Eulerian. However, you can easily visit all the cities and come back, right? So you can start from A and visit B, D, C, and then come back. So that's definitely Hamiltonian. So this is an example where the graph is Hamiltonian. There exists a path that visits every vertex exactly once and then come back. But it's not Eulerian, meaning that you have odd degree vertices, right? Um, Now there's like one case where it's obvious that it can't be Hamiltonian. If you have the same graph like that, same graph as what I just drew, but let's say there's a city E. Now, you can have a Hamiltonian path by starting from E and then go D, A, B, C, right? But it cannot have a Hamiltonian circuit because if anytime if you started from E, then when you come back, you have to go through city D twice, right? Yeah. And if you start from some other place, say C, then at any time you visit E, you have to again visit city D twice, right? So this right here is what's known as a bridge, meaning that if this is cut off, then now you have a graph that is not connected. Okay. So if you have a connected, of course, to be Hamiltonian, you need a connected graph because like to visit every vertex, it has to be connected, right? If you have in a graph an edge that's a bridge, meaning that if you cut it off, then the graph becomes disconnected. Like things in here and there cannot be connected anymore. If that ever happens, then it's not Hamiltonian. Okay. So like there are 2 ways to talk about this. It's one way to say that a graph that has a bridge cannot be Hamiltonian. I know what 75. Okay, 75 okay. And another way to say it is like notice that if that's what it is, then E is just one connected, like there's only one edge coming from E, right? If that happens, that becomes a bridge. So you can say that Hamiltonian graphs are at least 2 connected. Okay, so the edges, so from one vertex, you need at least 2 edges coming out. That's what it means to be 2 connected. Okay. Yeah, so it's talking about the same thing in 2 different ways. But sadly, that's about it. We don't really have an easy characterization of when an Eulerian, when a Hamiltonian path or Hamiltonian circuit exists or not. Okay. Eulerian path, it's a solved problem. You can just count the degrees and immediately you can say it has an Eulerian path or not. Hamiltonian, not so. But if you think about it, Hamiltonian is really the one that gets asked more often, just like the traveling salesman problem. You want to develop an itinerary that's the most efficient one. Usually you don't care about going through every possible path. That's usually wasteful, right? Usually what you want is to visit all the places, which means visit all the nodes, but you don't want to visit them twice. It's just you visit them exactly once. And Hamiltonian problem is not so easily solved, and in fact, one of the next classes that the data science majors are going to take are called data structures and algorithms, and over there we'll talk about some algorithms that could like figure out whether a given graph has a Hamiltonian path or Hamiltonian circuit.
Wait, so that one is Hamiltonian.
This is Hamiltonian because you can go through A, B, C, A, B, D, C, and then come back to A.
But for that one, can you just go to E, A, B, C, then go back to D?
That would have a Hamiltonian path,
Oh, yeah.
but it doesn't have a Hamiltonian circuit.
You have to go back to where you begin.
Yeah. For a graph to be called Hamiltonian, it has to have a Hamiltonian circuit. All right. Okay.